we've got two objects here, one rock or a ball or something, moving towards the second. We'll call this object number 1. We'll call this object number 2. We'll say that object number 2 is at rest, and it's struck by object number 1 as object number 1 is moving to the right. What's going to happen to object number 2 as it gets struck by object number 1? What's going to happen to it? Was at rest. It's probably going to start moving, maybe. Object number 2 will gain momentum. There'll be an impulse experienced by object number 2. We'll call that the impulse, or delta P, for object number 2. What's going to happen to object number 1? It's probably going to slow down, right? In other words, there's going to be a change in momentum of object number 1 as well. There's also going to be an impulse for object number 1. Both of these objects will experience an impulse. Both of these objects will experience a change in momentum. Object number 2 gains momentum. Object number 1 loses momentum. Got it? All right, let's try another one. You got this big object. We're not going to call it object number 1 or object number 2 because it's just one object. It explodes. It explodes into two pieces. The first piece goes off this way, and then the second piece goes off this way. Object number 2 is moving. It wasn't moving before. That's an impulse, right? That's a change in momentum. Object number 1 wasn't moving. Now object number 1 is moving. That's an impulse, right? Every time you have an interaction involving 2 or 3 or 4 objects, each of those objects will experience an impulse. They will experience a change in momentum. But what I want to do with you today is kind of continue what we did with you yesterday, and that's analyze not the individual object, number 1 or number 2, but rather let's analyze the system, 1 and 2 together. If we analyze 1 and 2 together, or the system, as opposed to individual objects, then what do we know about the momentum? Well, if delta P up here was plus 10, then what's delta P right here? Minus 10. There's a change in momentum of both of those objects, but the overall change in momentum is 0. If this one has a momentum of 10, then this one has a momentum of, this one gained 10 units of momentum to the right, and this one gained 10 units of momentum to the left, or negative 10. In other words, there's a change in momentum of both of them individually. But if we look at the entire system, the change in momentum is 0. Yesterday, we defined a law called the law of conservation of momentum, which says in an isolated system, what do we mean by that again, by the isolated system? Yeah. Yeah, no energy, no mass, in or out. Essentially, the way we're going to distinguish whether something's an isolated system or not is look at the forces. If there's no external forces, it's an isolated system. If there's something like friction that's playing a part in there, then that's not an isolated system. Okay, any external forces, all bets are off. But in an isolated system, the total amount of momentum change is 0. In other words, the total amount of momentum remains the same. Individually, objects gain and lose momentum all the time. But as a system, the total amount of momentum will always remain the same, as long as we can account for all the forces. That make sense? We're going to write that slightly different than we have up here. Okay, it manifests itself most easily in an equation that looks like this. Pi is equal to Pf. The initial momentum equals the final momentum. And then what we do is just look at the system before and after the collision or the explosion, because we can do it in a collision or explosion. When the bullet hits a person, that's a collision. When the bullet is fired from the gun, that's an explosion, right? When two objects come together, or when one object splits apart into two or more objects. In both cases, the initial momentum equals the final momentum. And we got to look at the momentum before and after, and then count up how many objects we have. If we have 3 objects, then it's going to be M1 V1 initial plus M2 V2 initial plus M3 V3 initial. right? MV for each object that we have. If we have 14 objects, then it's going to be all the way up to M14, V14 initial. It's pretty rare that we have more than 2 objects. It's almost unheard of to have more than 3 objects, but it's possible to have 75 objects. You're just probably not going to see that because that'd be quite a bit of work to do, right? Then you can do the exact same thing after the collision or explosion. Look at how many objects you have. Did those 3 objects stick together and form one object because there's Velcro on them or sticky tack or something? All right, then we'll say MVF, one object, right? Momentum of one object is just MV. If there's still 3 objects going off in whatever direction, then we're going to say M1 V1F plus M2 V2F plus M3 V3F. If 2 of them have stuck together, then we'll just have 2 terms after the collision. Basically, if you're looking at a collision or an explosion, 2 objects come together or 1 object splits apart, then you can say PI equals PF. If you're looking at the whole thing, if you're looking at one of the objects within that, then you got to look at impulse, right? But if you're looking at the whole thing, you're going to say PI equals PF. Count up the objects before, put MV in for every object. Okay, count up the objects after, put MV in for every object, and then plug in your numbers and solve. Last night we had 2 questions for homework on page 477. Both of these involved this conservation of momentum, this new technique that we're using to solve collisions. Right? Understanding, accepting, using the fact that the total amount of momentum will remain the same. Is there any issues with either of those 2 questions? Guys feel good about them? All right. Okay, let's take a look at another example then. Question says, a basketball player and her wheelchair, player A, have a combined mass of 58 kilograms. She moves at 0.6 meters per second to the east and pushes off a stationary player, player B, while jockeying for position near the basket. Player massive. Immediately after the interaction. For 2 weeks now, we've been talking about little things, right? What's the concept? Okay. Is there anything that we should circle with a red pen? Is there anything else that kind of jumps out at you? What do we know about this? Okay, tell me something. Tell me something here, other than a specific given. Okay, yep. Okay, we got an east and a west there, right? That's probably something we want to draw attention to with a red pen, for sure. Something's going to be positive, something's going to be negative. Some of you might even want to write positive and negative in here. Some of you, it may be enough just to circle it in a red pen. Okay, anything else? Got to be something else, because we haven't done anything yet other than identify something we could make a mistake on. Listen, Alex gave me a good thing to circle in a red pen, but in the end, if you don't have a concept here, it doesn't really matter if you circle anything in a red pen or not, because you're not going to do anything with it. What's the concept? What's the physics principle that's going to be used here to solve this problem? Yep. PI equals PF, conservation of momentum, right? Because in the end, it's a collision, right? You got one basketball player moving, hits another basketball player, pushes off another basketball player that's at rest. So let's say, we'll make a little note here, PI equals PF. You might not want to make that note. That's okay if you don't, but maybe it's helpful for you later on. Now understand that we could technically analyze this using impulse. How do we do this using impulse? How would the question change? If we're analyzing using PI equals PF, which is what Michael said, then we got to analyze the system, both basketball players together, right? If we analyze it using impulse, then we should do what? Analyze one or the other, but not both at the same time. Okay, does that make sense, guys? I'd probably go with conservation of momentum here. I think it's a little bit easier to do, but impulse is correct as long as you pick one object and not both. All right. Anything else here? Yeah. There's a stationary thing. Okay, it doesn't tell me a given there. Okay, I'm going to write that down as 0 meters per second. Okay, I mean, that's a given. VI is 0 meters per second, but it's one of those read between the lines givens, so that's a good one. Wheelchair. Sometimes what we want to do in situations like that is make it two objects, right? Well, you got a basketball player, you got a wheelchair, M1, M2, right? But they always stay together through the whole problem, so let's just treat that as one object. Basketball player and her wheelchair have a combined mass of 58 kilograms. Let's say M1 is 58 kilograms. Player B in her wheelchair is 85, so let's say M2 is 85 kilograms. You could circle that, okay, identify that, that's fine. Okay. I find it sometimes in these conservation of momentum problems, the givens get a little cumbersome, so we start circling them as opposed to writing them like this. Sometimes it gets a little bit cumbersome, but whatever works for you. What else we got? Something's 0.6 meters per second. What is that? It's the velocity, right? Is it V1 or V2? V1, V2? Doesn't. V1, V2. Yeah, it's going to be V1. Good. Is it going to be V1 initial or V1 final? Tony, V1I or V1F? Is this before Chicoides or after? Before. Okay, before. Yeah, let's say V1I. What else we got here? We got a 0.2. Oh, we got a 0 meters per second. What's that? Velocity. Yeah. Good. It's object number 2, initial velocity. That's what Bryce was saying. Specifically as a given, right? After the interaction, we're going to call that V2F, right? V2F. Now, I covered up this stuff down here because in the end, I copied out too much when I copied it from that slide here. Basically. Somebody said the concept that applies here is PI equals PF. So let's write that down and start counting up the number of objects that we have before the collision and after the collision. How many do we have? Let's put in a term for each of those. M1 V1I plus M2 V2I. How many objects? I think in the problems you had last night, they always stuck together, didn't they? Okay, so it was always one object after the collision. Now they stay apart. So now it's two objects. No big deal. Just an extra term, that's all. M1 V1F plus M2 V2F. Okay, does anything cancel there? Yep. M2 and V2. Okay. M2 V2I. Okay, we're going to cross that off. Not canceling. Right? Canceling means it can disappear from both sides. But yes, that does disappear. Bryce, tell me why that disappears. Good. Object. Okay. Player number 2 in a wheelchair isn't moving before the collision takes place. So anything, whatever M times 0 is. Good. happen. Probably kilograms, right? That's a standard unit. Look what would happen if you use grams. Say it's 30 grams and 30 grams and 40 grams, let's say. What happens to the grams? You can actually use other units in these problems. You don't have to convert to kilograms. You don't have to even convert to meters per second in these problems. I probably would, just as a matter of habit, because in everything else you have to, right? But these ones, the units end up canceling out. Okay? You get away with it if it's not in kilograms. All right, let's start plugging in some numbers and see what we get out of this here. M1 is 58 kilograms. V1I is 0.60. Bryce already told me that this disappears because V2I is 0. M1 is 58 again. V1F is negative 0.2. That negative is pretty important there. M2, 85 times V2F. So let's pull out our calculator on this. And let's start calculating some things here. Let's say 58 times 0.6, okay, that gives us 34.8, equals 58 times negative 0.2, negative 11.6 on the right side, plus 85 V2F. What goes over to the left side? Is it the 11.6 or is it the 85? Is that the 11.6 or the 85? The 85? The 11.6, yeah, good. It goes over by, good, by adding. So that becomes, what, 44.6, 45.4? Positive 45.4? And then we're going to solve for V2F by dividing, right? Let's say 45.4 divided by 85. 0.53 meters per second. Is that okay? Would you expect it to be a positive number? Look at the diagram. Okay, player B pushes away from player A. Okay, player B is on the right-hand side. Player B, which way does she go after she pushes? She's going backwards, right? But backwards for her is to the east, right? So it's going to be a positive value, yeah. Okay, let's try page 478 there. See what you can do with those. I'll give you a few minutes to work on them, and looks like we should have time to finish those in class today, and then we'll take a peek at what you need help with. Look at, forgot to, There's a, yeah. All right. One of the other questions you were just working on, you had a transformation event. One of the other questions you had a car in the car. Person. So again, So there's a lot. Maybe you want to know something like that sometime. But there are real applications for stuff like this. Imagine you're a investigator, police officer. You're not going to calculate the final velocity of a car after a collision, right? The initial velocity. So you're going to use skid marks. Let's try these two questions, please.